And here we go. I think recording is running. Oh, wait, there's one more. I thought I had disabled the waiting room, but okay, here we go. What are we going to do today? Today we're going to be talking about stationary sets most of the time. And the question, of course, is what are stationary sets? Well, I wanted to know actually where the name stationary came from. So I looked it up. And there is a paper by Gerard Bloch from 1953. And here you see the things that we will be talking about today in a more, we will talk about them in a more general setting. And, but okay, if you don't read French, we'll just read along. The first thing that Bloch defines is regressive function. Function on what? Well, it's a set O, and O is the set of countable ordinals in Bloch's paper. So, but in general, we'll be talking about subsets of cardinals, and for most of the time today, kappa will be regular, uncountable, if there is any deviation from that, I'll make that explicit. So what makes a function regressive? A function is regressive if it looks down, if f alpha is less than alpha for all members of the domain, except of course 0, because it's hard to find an ordinal less than 0. And if you look at Bloch's formulation, it's kind of interesting. He says that the function is regressive if f of x is less than or equal to x for every a, but then he said equality is excluded for the minimum ordinal, and in Bloch's idea, the minimum ordinal, the smallest ordinal is 1. There are people who thought that 0 didn't count as an ordinal in those days. And then there is the definition of stationary. I'm not going to use this definition, so I'm not going to write it down right away. He says, well, a set is stationary if every regressive function has this rather strange expression, the limit as x goes to capital omega, x in A is less than omega, capital omega. Well, capital omega is what very many people, including Cantor, used for omega 1. Omega 0 was lowercase omega, and capital omega tended to be used for omega 1. So that's why I said we're working on omega 1 here. And this whole limit affair, well, Bloch explains it in this next sentence. He says there is a point where the preimage is uncountable. So he says, I call a subset of omega 1 stationary if every excuse me, regressive function is constant on an uncountable set. That is what stationary means for Bloch. Like I said, I'm not going to use that definition in the rest of today's lecture. I'm going to use Bloch's characterization. The theorem he has here, he says, well, a necessary and sufficient condition for a set to be stationary is that every closed set in its complement is at most countable. So is at most countable. Okay. What does that mean, closed? And that is what I'm going to talk about today for the first part of the lecture. What are those closed sets and what can we do with them? And then I'll define stationary, and then Bloch's theorem will come back, but in a stronger version. We will see that towards the end of the first hour or in the beginning of the second. By the way, this notion that a regressive function is constant on a large set is already quite old. I put this here just for fun. I'm not going to expect you to be able to read this, but this is there is a famous paper by Alexandrov and Horizon in General Topology about compact spaces. And in an appendix of that paper, there is this theorem. This is in Russian. I know it's hard to read, but if you look closely, you will see that there is something about alphas in omega 1 going on. You see a mu alpha, and you see that mu alpha is less than alpha for all the alphas in omega 1. Hey, that's a regressive function. And then you can sort of see the conclusion. It says, well, there are alpha 1, alpha 2, alpha lambda, lambda less than omega 1. So omega 1, many alphas. And what do the alphas have in common? Their function values are the same. So this is a special case of what Bloch defined already. If you have a regressive function on omega 1, then it is constant on an uncountable set. Alexandrov and Horizon use this in general topology in all kinds of examples. I'll mention a few of those later on, but this idea is already quite old. That people try to look at functions that look down on cardinals. Why do I look at uncountable cardinals in this case? Well, this is not going to work on omega 0, on omega. You have a regressive function there that is injective. And if you forget about 0, then it's really injective. And if you really want to, you say F0 is 0, and then it's injective except for 2 points. So But if you try to do this on omega 1, and presumably Alexandrov and Eurozone tried this very hard, and then suddenly they realized, oh, it's not going to work, and then probably they found their proof. So, like I said, regular uncountable cardinals, and we need to know what closed means. We call a set closed, completely ordered theoretically, if this happens. Whenever you have a subset, the subset itself could be unbounded, could be cofinal. But if you look at an initial segment, non-empty, and then the supremum of that initial segment has to be in the set. For those who know a little bit of topology, on sort of an exercise. So I'll put this in brackets. If you don't know general topology, don't worry, you don't really need it. But if you do, you can define a set to be open if this happens. So this only makes sense for alphas bigger than 0. But those are the points where the interesting things happen. Anyway, this defines a topology, a true, honest-to-God topology on kappa. This is the order topology. It's very useful for general topologists, believe me. And what I just defined to be closed here is actually closed with respect to the order topology. So if you know about this, then life is just a tiny little bit easier for you. And if you didn't, don't worry, we're not going to use a topological language anyway. But anyway, we know what closed is. If you have a supremum, every supremum of every initial segment belongs to the set. And the important thing that we'll be talking about for the rest of the time is the notion CUB, C-U-B, closed and unbounded. This is an abbreviation you see in many papers. If what? Well, if it is closed and unbounded, okay, let's use the older word. If it is closed and cofinal. Well, there are, in the group interaction, you'll be asked to consider various subsets of regular cardinals and to see whether they are closed and unbounded or not. Okay, I'll give away one. Kappa itself is of course closed and unbounded. It's closed in the, it meets all the requirements and it's cofinal in itself. Another easy case, of course, is you take any ordinal and you take the final segment. That will be closed and unbounded as well. And there are various other relatively easy examples of those. And now let's go back up a little bit to Bloch's theorem. Look at the theorem. The theorem says a set is stationary if every closed set that is a subset of the complement is countable. Well, if we're talking omega 1, that means that countable and bounded is the same thing for a subset of omega 1. So what does stationary mean? What does characterize stationary here? Is every closed subset of the complement is bounded. So what will be our definition of stationary? A little bit more, should we say, affirmative. So Bloch's characterization of stationary we now use as a definition. We could formulate this we can sort of turn this around a la Bloch, and we get every closed set that is disjoint from S has to be bounded. That is what stationary means. And now the question, of course, is going to be what sets are stationary? And can we prove this lemma of Bloch for those stationary sets? Well, yes, but we need to do a little preparation here and there. The first thing that we do is look at some properties of the family of closed and unbounded sets. The first thing is, if I have two closed and unbounded sets, oh, wait a minute. I got ahead of myself. You can now guess what is coming. If I have two closed and unbounded sets, then their intersection is closed and unbounded. Why is this important? Well, so we can now conclude that we know many stationary sets, namely the closed and unbounded sets. Why? Well, every closed unbounded set intersects every closed unbounded set, apparently. And there you have it. It meets the definition, it satisfies the definition of stationary. But how do we prove that any two closed and unbounded sets intersect? Well, like so. We have to show that C intersect D is closed. Well, if you believe the topological characterization, then this is clear. The intersection of any family of closed sets is closed in a topological space. But if we don't know, well, then we take an alpha and look at and assume that the intersection is non-empty. Well, then we know that the intersections C intersect alpha and D intersect alpha are non-empty as well. But we're going to be looking at the supreme. We don't know that alpha is the supremum of C intersect D intersect alpha, but we know that there is a supremum because we're working in kappa in a well-ordered set. Look at this supremum. Well, look at C intersect beta. What can we say about this? Well, C intersect beta contains the intersection of C, D, and beta, which happens to be the same thing as alpha, because beta is the supremum of C intersect D intersect alpha. So between beta and alpha, there is nothing in the intersection of C and D. So these two are the same. And of course, this is a subset of beta because it's the intersection of beta and something. But beta is the supremum of C intersect D intersect beta. So beta is also the supremum of C intersect beta. The larger set C intersect beta has a supremum that is at least as big as beta, but it cannot be bigger than beta because it's a subset of beta. Therefore, it is equal to beta. So beta is a member of C because C is closed. And also for beta, the supremum of C intersect beta belongs to C. And of course, likewise, beta belongs to D. Okay, I did this a little bit extensively, but now we know that the intersection of two closed sets is closed. And in a similar way, you can prove that the intersection of an arbitrary family of closed sets is closed. Okay, closed. Now we need to show that it's unbounded. Take an alpha in kappa, and we need to find, I don't know, what shall we call it, beta in C intersect D above alpha. Well, that's easier than you might think. And all of this because we are working in an uncountable regular cardinal. We have alpha. Now, C is closed and unbounded. So we take the minimum of C, of the members of C that are lying above alpha. So gamma 0 is the minimum member of C that is bigger than alpha. And what is delta 0? Delta 0 is the minimum member of D that is bigger than gamma 0. And well, you can guess where gamma 1 is coming from. In general, and I'm going to do that in color. Whenever we have a delta that goes with a number n, I take the next gamma bigger than that delta, and in the same way, okay. So this is how this is going to pan out. We find a sequence. Oops. We find an increasing sequence that visits C and D alternatingly. Gamma 0 is in C, delta 0 is in D. Gamma 1 is in C, delta 1 is in D, and so on. That's a countable sequence. So what do? Where does our beta come from? Well, beta is the supremum of this countable sequence. This countable sequence has a supremum that is really smaller than kappa, but it's bigger than alpha. And beta belongs to C because it is the supremum of a subset, a bounded subset of C. And it belongs to D because it's the supremum of a bounded subset of D in kappa. And there you have it. It's the supremum of this bit, it's the supremum of that bit, therefore it belongs to the intersection. So now we know the closed unbounded sets are closed under finite intersections. Because if the intersection of two closed unbounded sets is closed unbounded, by induction, the intersection of arbitrary finitely many closed unbounded sets is again closed and unbounded. But we can do much, much, much better. Take a family of closed subsets of cardinality less than kappa and enumerate it using a cardinal or an ordinal less than kappa. Then this intersection of this family of closed unbounded subsets is again closed unbounded. So not only 2, 3, 4, 5, 6, but if we're looking at omega 1, countably many closed unbounded subsets have a closed unbounded intersection. If we are looking at omega 2, if I take omega 1 many closed unbounded subsets, I get a closed unbounded intersection. Take your favorite uncountable regular cardinal, take fewer than that many closed unbounded sets, the intersection is closed unbounded. That's a very strong property, very useful in very many circumstances. And I'll try to mention that some examples of that later on. So how do we prove that? Why is it closed? Well, in this case, you can simply copy the thing for 2 closed unbounded sets, because remember how that went. we found out that beta, let me underline this, we found out that beta was the supremum of the intersection of C and D and beta. Now, replace C intersect D with the intersection of the family that we're talking about. So beta is the supremum of the intersection of beta and the intersection of all those C alphas. Then you prove in exactly the same way that beta is the supremum of C alpha intersect beta for each individual alpha. Therefore, it belongs to each individual C alpha, and we're done. So I'm leaving that to you. I'm leaving this for you to check because it's not very difficult. And I could also leave it to you to check that the intersection is closed and unbounded. Why is that? Well, not fix, that's a bit too much. We can actually copy the same proof. If you're, we take some gamma, no, not gamma, that would be, we take a beta less than kappa. Now, beta is less than, well, we look at C0. We take the minimum member of C0 that sits above beta. Then we take gamma 1, 0 above gamma 0, 0, but we take it from C1. And we use our enumeration of the sequence of C alphas, and we keep picking the minimum member of C alpha that is bigger than the one that came before. Why can we do this? Well, kappa is regular. And if I have taken these gammas here, then I have taken less than kappa many gammas. So their supremum is less than kappa. And we can keep on going. And then we take gamma 1, 0 wait a minute, gamma 0, 1, I'm sorry. We take gamma 0, 1 above all the gamma alpha zeros. And that is possible because kappa is regular and bigger than lambda. The cofinality of kappa is bigger than lambda, and so we can keep on going. Well, now you see what is going to happen. Delta to be what? Well, we have very many gammas, but we can say delta is the supremum of gamma 0 n. This column here this column, whoops, this column has a supremum, and it's delta. This column has a supremum too, but it's the same delta because they are intertwined, just like in the case of two closed and bounded sets. This column has the supremum, it's the same one because all those sequences, all those columns are interlaced. So this is not only it's the supremum of the gamma 0 ends, it's the supremum of the gamma 1 ends, it's the supremum of the gamma alpha ends for every alpha less than lambda. So delta belongs to C0, delta belongs to C1, delta belongs to C alpha. And there you have it. We have delta way bigger than beta, and delta belongs to the full intersection of the C alphas. And there we have our closed unbounded sets. And so the family of closed unbounded sets is apparently closed under intersections of fewer than kappa many sets, which is a pretty strong property. And if we take all the sets that are bigger than closed unbounded sets, there may be very many closed sets that are not closed unbounded, but that contain a closed unbounded sets. This is what is generally known as this is what many people know called the cup filter, and others also call it the club filter. Because there are people who take the first two letters of closed and those two letters from unbounded and call the sets club. It's a filter. What does filter mean? Well, if you take two members, then the intersection of the two members is again a member of the family. And this is what defines filter, these three properties. You can look it up in Jech's book, but maybe you have seen this already in other circumstances. And this filter is kappa complete. And what does kappa complete mean? Well, closed under intersections of fewer than kappa many members. So if you have, we're not asking that if we take kappa many members, then the thing has an intersection that is still in the family. We want small families to have an intersection that are still closed and unbounded. We shouldn't expect big families to have a non-empty intersection, because if I take the interval from alpha to kappa and everything above, including and above alpha and less than kappa, then I get an empty intersection. So if I take kappa many closed unbounded sets, then I might be very unlucky and get an empty intersection. Now, okay, it's almost time to a break, but I want to go on just a little longer and complete what we need to know about closed unbounded sets, and then we can jump into the stationary sets in the next hour. So bear with me for a little while. We can make some kind of sort of intersection of big families anyway. And that's the this one. What on earth is diagonal intersection? Well, let me show you. Well, okay. I said family, but family is not the right word. It really must be a sequence. The indexing is important here. When we did the intersection of two closed sets, it didn't matter who was the first, who was the last. When we did the small family, it didn't really matter who was the first or the last in the enumeration. The enumeration was useful in the proof. But here the enumeration is part of the statement of the theorem, and the theorem is this. Look closely. We look at the deltas in kappa that have the following nice property. They belong to all the C alphas where alpha is less than delta. I'm not saying that delta belongs to C delta, because that doesn't need to be the case. I'm just saying that all the C alphas that have a small index contain delta. Notice that the intersection of all the C alphas where alpha is less than delta is cup, because delta is less than kappa. But delta is so special that it is in that particular intersection. So the indexing really matters in this case, because if I would permute the C alphas, then this particular diagonal intersection would be completely different. So this is the diagonal intersection with this nice delta on top of it. And what does the theorem say? This diagonal intersection is also closed and unbounded. Now, that's a remark. This is nothing topological. This is really combinatorial. And so we also have to prove that it is closed. And I hope I have the, yeah. So suppose Suppose that delta is the supremum of delta and the intersection of delta and that thing. So we must show that for every alpha less than delta, delta belongs to C alpha. Okay, well, let alpha be less than delta. Then also, if we take an initial segment away from a set, then the supremum doesn't change because the supremum only depends on the final bit. So we know that delta is also the supremum of this. But if beta is in that intersection, oh, wait a minute, that was unfortunate. Okay, the alpha was already an index and I don't want to mix too many letters here. So if gamma is less than delta, we need to find, to show that delta is in C gamma. Well, if beta belongs to this set, then beta belongs to C gamma because beta is in this diagonal intersection and gamma is less than beta. Ah, so delta happens to be the supremum of C gamma intersect delta, the interval delta gamma. Every member of this thing sits in C gamma, so delta is the supremum of that stuff, so delta belongs to C gamma. Gamma was arbitrary, so there. Delta belongs to that diagonal intersection. Unbounded, okay, let gamma less than kappa. And now we are going to sort of, let's go back to what I just said a few moments ago. If I take some element of kappa and I intersect all the C alphas where the index is less than that member, so in this case that was delta, then that set is cup. Okay, lovely. We're going to be using that. So we look at the intersection of the C alphas where alpha is less than gamma. That's a closed unbounded set. Delta zero, gamma is some member of kappa, so there must be something above gamma in that intersection. Let's take the minimum. we do the same thing. Now we take the intersection of all the C alphas where alpha is less than delta 0, and let delta 1 be the minimum of that, but keep it above delta 0. Now you see where this is going. We find delta n plus 1 to be, we take that in the intersection of all the C alphas where alpha is less than delta n, and so on. And now we take the delta that we're looking for to be the supremum of the delta n's. And so delta is bigger than gamma, that's for sure. And what else? Now take alpha less than delta. Then there is an n such that alpha is less than delta m, because the sequence of deltas increases cofinally to delta. But then by construction, well, let's be careful. For every n bigger than m, alpha, delta n belongs to C alpha. Okay, so delta belongs to C alpha, and that is what we want to have. Our diagonal intersection is again closed and unbounded. And okay, we'll have a break now, and I'll pause the recording in a moment, but during the break, you can make all kinds of variations on this, but these three are easy cases of diagonal intersection. And I can promise you the intersections will all be different. Okay, and now I want, right. I pause the recording and we'll continue in about 15 minutes. There we go, it works. So during the break, we found out what those diagonal intersections were. Somebody fell into an existential crisis. Well, good luck with that. You can get the limits of the limits if you would take the open interval from alpha plus omega to kappa, because then delta would have to be bigger than all the alpha plus omega, where alpha is less than kappa. Then you get the limits of limits, and so on. Okay, now we go back to Bloch's theorem, which characterized his stationary sets in terms of intersecting every closed and bounded set. And we're going to do the theorem that makes stationary sets so important. That is Fodor's pressing down lemma. This is this is the central result about stationary sets. It is what gives them their power, and basically all the applications that you can think of sort of revolve around this idea at one time or another. And it's stronger than what Bloch concluded. If you have a stationary subset, kappa is still regular uncountable. Okay, this is the theorem. If you have a stationary subset of a regular uncountable cardinal kappa and you have a regressive function on that, so f alpha is less than alpha all the time, except for alpha equals 0, then you can find a stationary set which is a subset of S. So you shrink your given stationary set to one that is still stationary, on which the function is constant. I cannot begin to name all the applications of this because, like I said, set theory is sort of full of them. But I'll mention one or two later on. So how does the proof go? Well, if you're an intuitionist, look away now, because suppose not. We are not going to construct the constant value that we are looking for. We are simply asserting that if there isn't one, then we get a contradiction. The proof is actually quite short, but nevertheless, but we did a lot of work beforehand, so maybe we are due a short and not too difficult proof. Suppose not. Well, then for every alpha less than kappa, if we do suppose not, it simply means that for every alpha less than kappa, this particular set is not stationary. That is what we are saying when we say suppose not. Okay, that means we get, and here again we use the axiom of choice, a sequence so let's call this set T alpha. T alpha is all the sigmas that are mapped to alpha. Well, T alpha is not stationary. That means there is a closed unbounded set disjoint from it. Well, okay. Right? This is what we get. Now, what can we do with this? Well, we can do at least one thing. We can take the diagonal intersection of all those C's. We have just proven that this diagonal intersection is cup again. Our set was stationary. We have a closed unbounded set. Better take a point in there because at least we have that. And now what happens? And we take the sigma non-zero, of course. Zero is not really important. So F sigma is less than sigma. That means that sigma is a member of the set T with index F sigma. That's the definition. T alpha consists of all the sigmas whose image is alpha. So T of F sigma is all the members of S that have F sigma as their image. And also because D belongs to the diagonal intersection of all the C's, we find that sigma also belongs to the C that goes with F sigma. Let's make that sigma clear. And there is our contradiction. So the proof is very short. Well, given all the work that we did in the previous hour. Without that work, we would have to build all that from scratch, and then the proof would be as long as the previous hour. Stationary sets have this particular remarkable property. If you try to look down from each member of a stationary set, then you're going to be looking at the same point from many levels in the stationary set. This result is really, really central. A major application, which I won't have time for, but if you feel like reading something else, there are more theorems of Silver, but the theorem of Silver that I'm talking about now is in the very chapter that we are reading. So you start reading at page 96, and what you will see there is this. If kappa, okay, this is one of the exceptions, is if kappa is singular and the cofinality of kappa is uncountable, and 2 to the lambda is equal to lambda plus for all. So suppose you know that the generalized continuum hypothesis holds for all cardinals less than kappa, and kappa is singular and of cofinality and of uncountable cofinality, then Silver's theorem says, okay, the generalized continuum hypothesis also holds at kappa itself. This is one of the things that I didn't mention last week, because it wasn't as elementary as the things that we talked about last week. This theorem is also a sort of a restriction on the possible behavior of cardinal exponentiation of the continuum function. It tells you that if you have a long stretch of the generalized continuum hypothesis and the stretch is singular of uncountable cofinality, then you will get it for one more. This was a big surprise in the 70s when it was proven, because people thought that you only had freedom on regular cardinals, that the freedom that you had for regular cardinals was also available for singular cardinals. And the conclusion was, no, it isn't. Something strange is going on with the continuum function at singular cardinals. And this is one of the first instances of that. And the proof that you will find in Jeff's book really uses the pressing down lemma a lot. It takes 1 or 2 pages, but and it only does it, the book does it for the specific value. That's just to keep the notation a bit clean, but you can do this for any singular cardinal of any uncountable cofinality. Anyway, from now on, kappa is regular uncountable again. Oh, what about the converse of Fodor's theorem? Well, of Bloch's theorem as well. The pressing down lemma is generally abbreviated PDL. If S is cofinal, but not stationary, say S intersect C is empty and C is a cup, then you define F from S to kappa by saying you take the maximum of C intersect alpha. That's a maximum. That supremum is a maximum. It belongs to C and it is smaller than alpha. This function is regressive and only constant on bounded sets. So the pressing down lemma is an if and only if. If you're stationary, then regressive functions are constant on stationary sets. If you're not stationary, there are regressive functions that are only constant on bounded sets. So let's see if I have still more paper. Okay, now there is an issue that I've been skating around for a bit, but we'll get to it in a moment. No, we'll get to it now. We have seen in the beginning closed unbounded sets are stationary. One question that we haven't answered, and for all we know, this might be the case, and then you may ask, why did we define stationary sets at all? Is it perhaps the case that stationary sets are so big that they actually contain closed unbounded sets, and we are only talking closed unbounded sets essentially here? The answer is no, definitely not. There is an easy answer for omega 2, or in general, we look at E0 E0 is the set of all ordinals of cofinality omega, and E1 is the set of all ordinals of cofinality omega 1. Now, these two are stationary. If you have a closed unbounded set in omega 2, then you keep walking. Does it have an element that has countable cofinality? Yes. Start enumerating E0. Take your closed unbounded set, take the isomorphism between the closed unbounded set and omega 2. There is only one. We have learned that well-ordered sets, if there is an isomorphism, there is only one. And cofinal subsets of omega 2 are isomorphic with omega 2 because omega 2 is regular. So take the counting function of your closed unbounded set and look at the image of omega 0. That is a member of E0 intersect C. Take the member with number omega 1, that is a member of E1 and your closed unbounded set C. There you have it. But these two are disjoint sets. They are both stationary. Neither of them is in the closed unbounded filter. Actually, this is easy. For all kappas bigger than or equal to omega 2, if lambda is smaller than kappa is regular, then E kappa lambda, those are all the alphas less than kappa whose cofinality is lambda. This is stationary. So if we are looking at omega 3, then we can find 3 easy disjoint stationary subsets. We're looking at omega 4, we have 4 of them. If we're looking at aleph omega plus 1, we have infinitely many disjoint stationary sets. And that really destroys the filterness of the family of stationary sets. You can find many disjoint ones. How about omega 1? Well, homework. I'm going to prove a bit more, but in the homework, you find a reasonably elementary construction of 2 disjoint stationary subsets of omega 1. But it needs choice. And in fact, if you were to do another course on some highly non-trivial descriptive set theory, there is a model of set theory in which the closed unbounded filter is everything, so to speak. For every subset of omega 1, either it or its complement belongs to the closed unbounded filter. So in that particular model, there are no disjoint stationary sets, and the axiom of choice fails miserably there. All right, but we're going to use the axiom of choice we are going to use the full force of it because there is a theorem due to Solovay. Okay, before, no, there's a theorem due to Solovay that says if kappa is regular, I'm reiterating this for emphasis. Here is the theorem. Solovay proved this somewhere in the 60s, if I'm not mistaken. You can split every stationary set of every regular uncountable cardinal into kappa many stationary sets. So those two disjoint stationary sets on omega 1, that's peanuts. Even if we're looking at omega 1, we can split every stationary set into omega 1 many. But as you will see, that takes a little bit more work than the construction that you will see in the homework of those two disjoint ones. We're going to do this in a few steps, but I want to, let's say, point point you in another in the direction of another proof, but that only works if kappa is a successor cardinal. Then this was known already, and the proof is somewhat easier than the one that I'm going to give now. If kappa is a successor, then you can find a completely different proof than the one that we're going to give here, based on what is called an Ulam matrix. And Ulam found those matrices already in the 20s or 30s in an investigation into measures on cardinal numbers. And he used his matrices to prove that certain things were impossible. But we're going to give a sort of a unified proof of this fact. So how do we start? Step one. Suppose S is our stationary subset, happens to be a subset of E. Let me get the. Suppose S is a subset of E kappa omega. So every member of S has countable cofinality. So this would happen if we were talking about omega 1, kappa in the case kappa aleph 1. Here we go, we choose. And what is my notation? Sequences. let's call the sequence as alpha, increasing cofinal for every alpha in our stationary set. We choose sequences. For every alpha, we choose a sequence that converges to alpha monotonically, increasing and cofinal in alpha because the cofinality of alpha is omega. What do we do with it? We're going to do another suppose not, because we're going to claim this. There is an n such that for all eta less than kappa, the set okay, this takes a little bit, it takes a moment to chew on. The alphas go up to kappa, so they increase. Those sequences of betas, every beta alpha n sequence converges up to alpha. But if alpha gets bigger, of course, some of those betas will have to grow with them because otherwise the sequences cannot keep up with the alpha. I mean, if alpha is if alpha 1 is way smaller than alpha 2, then the sequence that goes with alpha 2 should at least rise above alpha 1 eventually. And so the beta alpha m's tend to get bigger. And the claim says there is even a fixed m such that the mth member of every one of those, of many of the sequences are already quite high. Okay. So many alphas each time that you have stationary many alphas where this happens. And how do we prove the claim? Well, we do the old suppose not trick. Take for every n in omega a cubset Cn and eta n less than kappa such that what? Now, such that this goes wrong, Cn is disjoint from the corresponding subset of alphas. That means if alpha belongs to Cn intersect S, then beta alpha n is less than eta n. So for all the alphas in that closed and bounded set that also belong to S, the nth term of the sequence stays below eta n. Okay. How does that help us? Well, we have countably many closed and bounded sets. We have an uncountable regular cardinal. We can take an alpha that belongs to the intersection of all the CNs, and of course it belongs to S. Okay. Then we get a problem. We know that beta alpha n for our alpha is less than eta n. So alpha is less than or equal than this particular ordinal, because alpha is the supremum of the beta alpha n's. And each individual beta alpha n is less than each individual eta n for the corresponding n. So alpha is less than or equal to that supremum. And that is a bit of a problem, because this would mean that S intersected this cup set this would mean that this set is bounded contradiction. Okay, how are we doing for time? I'll finish this and then we'll have our second break, and maybe then I'll have to rework the homework. We'll see where we end up with this. All right. Take our M. Take our M, and for the moment we will define S we fix our M and we take our function, we define a regressive function in this way. Alpha goes to beta alpha M. And here we see our stationary sets appear. Take, what is my notation? Take gamma 0 less than kappa such that T0 we have a regressive function, we have Fodor's lemma, so we know that the function is constant on a stationary set. Well, we can take gamma 0 to be the smallest value for which this thing is stationary. But we can put gamma 0 here. Okay, gamma 0 plus 1. We can look at all the alpha in S for which beta alpha M is at least gamma 0 plus 1. The set of all the alphas for which beta alpha M is bigger than gamma 0 plus 1 is stationary. Keep going. We are looking at a regular uncountable cardinal Suppose we are given an eta, and for all the etas less than psi, we have our gammas. But eta is still less than kappa. Let, for the moment, gamma be the supremum of all those gamma xi's, which is less than kappa. Now take gamma eta bigger than this gamma, such that T eta, which would be all the alphas in S, F alpha is equal to gamma eta, is stationary again. We can keep on doing this because kappa is regular, and at any given time, we only have a very short sequence of gammas. We can take something above it, and we can keep on taking those gammas, and we still have a substantial part of S, a stationary part of S, on which all those things are positive. And that gives us, oops. Why is this one as required? Well, the function f is constant on every t eta, and it's constant with different values for different t etas, and so the t etas are disjoint. They are stationary because we found them to be stationary, and there you have it. Okay, one last thing before we jump in, before we have our break, and before we jump into the final part of the proof. We did this for what was our case? Step one, suppose we have a stationary subset of just E kappa omega. And then we could do it. Okay, step two. Suppose we have another cardinal, not omega, but another regular cardinal, and we look at all the ordinals with that particular cofinality, and we have a stationary subset of that. Okay, same proof. Nothing really changes. So why didn't I write that down? Well, because I thought that maybe working with natural numbers looked a little bit more familiar. But if you go through this proof, we choose sequences and we replace omega by lambda. Increasing cofinal. The claim is there is an M in lambda. Suppose not, then we have lambda many closed unbounded sets such that all this happens. We get our contradiction still because the intersection is bounded. Then we work only with beta alpha M, and then the proof doesn't change after this. So same proof. If we have a stationary subset of some E kappa lambda, then we are done. So the problem is what to do if we have a stationary subset that isn't part of one nice station E kappa lambda. Then we have to do a little bit more work, but that work we'll do after the break. And now I need to pause the record. Okay, let's continue. I put in something that I almost forgot in the first hour even, but it is something that is very useful to know in all kinds of applications. If you have a stationary set and you write it as the union of fewer than kappa many subsets, then one of these lambda many subsets has to be stationary. Contrapositively speaking, if you take fewer than kappa many non-stationary sets, then the union is non-stationary as well. And this all relies on the fact that if you take fewer than kappa many closed unbounded sets, then the intersection is still closed unbounded. And that immediately proves the contrapositive statement, but it's this version, the one with if you take a small union of sets and the union is stationary, then one of the sets is stationary. That one is quite important in many cases. I also put another quote from Bloch's paper in there to show you that Solovey must have gotten some inspiration from somewhere. His theorem 2 states exactly, well, not exactly, it's the claim that we made a few moments ago, that there would be an n such that all those sets where the thing was unbounded was stationary. That is written down here in theorem 2, and it's sort of interesting that, okay, we don't put the proof here because we don't have the place for it, the room for it. But then here you will find that Bloch proves that if you take a stationary subset of omega 1, then you can split it in omega 1 many stationary subsets. So the theorem, the theorem in this shape was already known to Bloch. Okay, we were at step 2. Well, we did step 2. So what is step 3? Step 3 of our proof is, well, we are not a subset of one of the E's, or are we? Suppose S is a subset of all the ordinals that have cofinality smaller than themselves, the singular ordinals, so to speak. Well, then we have the fortunate situation that the cofinality function is regressive. Hence constant on a stationary subset. Say with value and then we're back at step 2. Because then we found the stationary subset of S, which is a subset of E kappa lambda. We split T, and whatever we do with the rest of the points of S, we can put them one by one with the other bits or whatever. But as soon as we have split a subset in kappa many stationary sets, then we can create a splitting of the big set in stationary subsets as well. So what case is left? Well, the case that is left is this. S is a subset of all the alphas that are equal to their own cofinality. Now, this is sort of an extraordinary case, because apparently the regular cardinals form a stationary subset of kappa. If they have a stationary subset and you make a subset a bit bigger, it's still stationary. What does that mean for kappa? Well, in the group interaction, you will be asked to reflect on this, but there is this type of cardinals has a definition. They're called Malo cardinals. Malo was a German mathematician, if I'm not mistaken. And he long ago wrote about this possibility already. But Malo cardinals are weakly inaccessible for sure, because as you will see in the group interaction, the set of limit cardinals below an inaccessible cardinal, for example, they form a closed and bounded set. So the successor cardinals are not stationary. That means that all these things will be regular limits. So there are very many regular limits already below kappa, and that makes kappa already quite big. But anyway, what do we do when we have this case? Because now we don't have a constant cofinality function anymore. We can use the same proof but with a few twists. The first thing that we do is we shrink S a little bit. We look at T, that's the alphas in S. And notice every alpha in S is a regular cardinal. So we can look at S intersect alpha . We can look at S intersect alpha and we can say, well, maybe, S intersect alpha can be stationary in alpha or not. And we take all the T's such that S intersect alpha is not stationary. And the claim is T is stationary. This is an interesting thing. You have a stationary set, and when you intersect it with smaller ordinals, you could think, well, maybe it's stationary too, lots of times. And the answer is no, it's not stationary lots of times. Okay. Take C, a cup. Let C prime be the set of limit points. And what does that mean? Well, alpha is in C prime if alpha is the supremum of alpha intersect C. That is what it means to be a limit point of the set. And that's exactly what happens in the topology. All the basic neighborhoods of alpha intersect C, and that means that alpha is a limit point of the set. C prime is closed unbounded. Again, if you know your topology, then yeah, of course it's closed. And is it unbounded? Yeah, because you can start at every point and you take an increasing omega sequence in C, and the supremum of that again belongs to C prime. So C prime really is closed and unbounded. And here is what we do. We take a point alpha in S and also in C prime, but we take the first one. So alpha happens to be in C2, but it is in C prime. So C prime is a subset of C because C is closed. And what can we say? Well, alpha is in C prime, so C intersect alpha is closed and it is cofinal in alpha. So it's a cup subset of alpha. C prime intersect S intersect alpha is empty. Why is that? Well, because alpha is the minimum of C prime intersect S. Anything below alpha is not in the intersection of both. And C intersect alpha is cup in alpha implies C prime intersect alpha is cup in alpha. Because we are only looking at the regular cardinals above. We're looking at regular uncountable cardinals in S. Okay, L of 0 could be in S, but we throw it out so that every member of S is a regular uncountable cardinal. And then alpha is regular uncountable, and if you have a cup set in alpha, then its set of limit points is again cup. So S intersect alpha is not stationary in alpha. So alpha belongs to T and alpha belongs to C, and there we have it. T intersects every closed unbounded set in kappa. So we work with T. What do we do? Well, T is stationary, and T itself is stationary. If alpha is in T, then alpha regular uncountable, and T intersect alpha is not stationary in alpha. For every member of T, T intersect alpha is not stationary in alpha because it's a subset of S intersect alpha. So what do we do? C alpha cup with C alpha intersect T intersect alpha is empty. Okay, what are we going to do with that? We take its enumeration, and in the group interaction, you're invited. I'm giving away an answer in the group interaction now, but still prove that enumeration has the property that is claimed there. So we take the increasing bijection between alpha and C alpha. So this is the difference with step 1 and step 2. We had just one single cardinal here that would work for all the sequences, but now the sequences get longer and longer and longer. The higher up we go into kappa. The sequence is increasing and continuous. And we used to call this normal a few weeks ago. Why continuous? Because C is closed. If I have an increasing initial segment of this enumeration, then the supremum of that initial segment has to be in C, so it has to be the number with the right index. What shall we say? Eta limit. And of course, alpha is the supremum of all those beta, alpha, gammas. And we get the same claim as before, but now there is a psi less than kappa, because we don't have a single alpha to work with, but all those psi's are less than kappa. So there is a psi less than kappa such that we do the same, we get the same conclusion as in the first steps. There is a single index such that for all ordinals below kappa, the set of alphas for which the xi term in the sequence beta alpha xi is bigger than eta is stationary. This is exactly the same claim as we had at the beginning. So the alphas that we're talking about are always bigger than the xi. And of course, then the proof finishes as before. Because then we can use exactly the same proof as before. We could get, we'd use the regressive function alpha goes to beta alpha xi, and we run it through the same mill as we did a few moments ago. All right, so once we have this, then we're done. So how do we get this? Well, as always, suppose not. That's what you do lots of times when you work with stationary sets and ordinals. You say there is a stationary set with this or that property, and then you say suppose not, contradiction, so there must be one. And we're doing the same thing. So no xi works. Well, okay. for every psi, take what? Well, take C psi a cup, and where is my such that things go wrong, which means that so for all the alphas in C psi, the corresponding beta is too small. It's smaller than gamma psi. Now, in the other case, we took the intersection of the C psi's, and that's not going to wash here. What we're going to do is take the diagonal intersection, but we need another intersection. We take all the deltas in our first proof, we could simply take the supremum of the gamma psi's, but the gamma psi's could be increasing too, for all I know. So we get two closed unbounded sets, and that this D is a closed unbounded set, you will be invited to look at in the group interaction. You can do it with another diagonal intersection if you want. So now what do we do? Well, T was stationary, right? So we take alpha less than delta, both in T intersect C intersect D. Okay, so both are in T intersect C intersect C. So they have those properties that we were talking about. Okay, if psi is less than alpha, then what happens? Well, beta alpha psi is less than gamma psi is less than alpha. Because alpha belongs to D, gamma psi is less than alpha, and because alpha belongs to C and psi is less than alpha, we have this. But also, oops, that's not what I wanted to do. But also, beta delta psi is less than gamma psi, well, still less than alpha. Delta belongs to D. Well, delta belongs to C, that's the important bit. It means that all the beta delta xi's are less than the gamma xi's, and well, because alpha belongs to D, we have this thing. And this is the important bit here. Because why? What does that mean? It means that beta delta psi is increasing of order type alpha, hence, and below alpha, hence, beta delta alpha is the supremum. Beta delta alpha, that is the supremum of this sequence because the sequence is continuous. C is closed. This is a sequence of things in C delta. And so beta delta alpha belongs to C delta. And the supremum is also equal to alpha. But what? Well, alpha belongs to T, and beta delta alpha belongs to C delta, and C delta intersect T is empty. So the point beta delta alpha belongs to C delta, the point alpha, but the point beta delta alpha does not belong to T, the point alpha belongs to T, and they're equal, and there's our contradiction. So we have shown, and so like I said, and the proof finishes as before, we have found our Xi and everything, and now you can split T into kappa many stationary subsets, like in the previous proofs. So this is an important result about stationary sets. It tells you that there is lots of variety among them, and it's also used in all kinds of structural things. I don't really have time to go into that, but I want to finish with, let's see if we have time there, we'll have time for that. Finish with one application of this, of the pressing down lemma again, that we will need in the near future. And that is this theorem. Theorem of Shanin's. It comes from topology and general topology, actually. Suppose you have an uncountable family of finite sets. And this is part of combinatorics, and combinatoric results tell us that there is always some nice regularity hidden in any big structure. And what is the nice regularity hidden in this structure? Well, there is an uncountable subfamily let's call it B, and there is a set, a finite set R, and why it is finite will become clear in a moment, such that if B1 and B2 are in B and B1, is not equal to B2, then B1 intersect B2 is equal to R. And here is the picture. Here is the set R, and all the other sets in the family B look like this. And so maybe I should erase the set R a little bit and give it a different color. All the sets in B have R in them and a little bit more, but all those little bits more are pairwise disjoint. And the Such a family where all the 2 by 2 intersections are the same is known as a delta system And Shanin's theorem is now generally known as the delta system lemma. Here is a proof using stationary sets and everything. Okay, A is uncountable, and if it should work for an arbitrary uncountable family, it should work for a family of size aleph 1. So we assume, why not, A has cardinality aleph 1. And because A consists of finite sets, we may as well assume that that all members of A are subsets of omega 1. We simply well order the union of A in type omega 1, or even smaller if there are many. No, we well order the union in type omega 1, and let's be done with it. And we enumerate A as, what letters did I use? I probably used alphas, why not? We enumerate A as A alpha, alpha less than omega 1. And we make a regressive function. So here is the thought. If you have A alpha, it could be a finite set. This bit could be empty. This could be empty, the bit to the left. But if it's not empty, we take the maximum, and that will be F alpha. And if this is empty, we simply take 0 as function value. Take S stationary. And beta such that F alpha is beta for alpha in S. Now we use Fodor's pressing down lemma. We could have done this with Alexandrov and Urysohn's lemma, by the way, with a little bit more work later on. So then we get this situation. Suppose we have an alpha and a gamma both in S, then this happens. The maximum of A gamma intersect gamma, oops, I'm sorry. This is the beta. The beta is less than alpha. So A gamma intersect gamma has its maximum in beta. A alpha intersect alpha has its maximum in beta. So there is nothing from A gamma between alpha and gamma here. And that's an important, so the rest of A gamma lives at gamma or higher. Okay. Now we have one more thing, two more things to do. First, the finite subsets of beta plus 1 is countable. Every one of these intersections is a finite subset of the ordinal beta plus 1. So for every x in that family, we have Sx. Those are all the alphas in S, for which A alpha intersect alpha is equal to x. The union of all the Sx's is equal to our stationary set S. Every member of the stationary set has its A alpha intersect alpha as a finite subset of B alpha plus 1. And now we get to the blue announcement from the beginning a few moments ago. Some Sx is stationary. We have countably many things. We have split the stationary set into countably many pieces. One of the pieces has to be stationary. Okay, next, we take a cup set This is a closed unbounded set. Again, I refer to the group interaction where you can ponder this for a moment. And now look at alpha less than delta in S intersect D. S intersect D is stationary, hence uncountable. So we get an uncountable family of sets. We have our X here. We have our alpha here. We have our gamma here. The rest of A alpha consists of a little bit of X and some more, but that some more sits above alpha, but it sits below gamma because gamma belongs to D. And the rest of A gamma is here. And there you have it. That's our family. This is our family B. These are the A alphas, where alpha sits in S intersect D. That is the family that we were looking for. I said this is an important result. Where are we going to use this? We're going to use it when we are doing the forcing, and we are going to need this in order to prove that bad things don't happen when we are using Cohen's forcing method in certain cases. I'll get to that later on. I still have a few minutes. I want to use a few minutes because this delta system lemma is quite general. You could say, well, what about countable sets? Well, you could do the same thing. Okay, uncountable should probably now be size L of 2 at least. We just kick everything up one cardinal. So if we have countable sets, then we had L of 1 finite sets. So L of 0 was sitting between the size and the number of sets that we have. Now we have countable sets, so we look at L of 2. And we can use the same proof we take the stationary set of all ordinals of uncountable cofinality, and then we run it through the same proof where we say that F alpha is the supremum of A alpha intersect alpha. A alpha is countable, its supremum is way smaller than A alpha, than alpha itself, because that's cofinality is omega 1. And we get the same situation as what I drew here. We get a beta. Now beta is not necessarily the maximum of the A gammas, but who cares? Everything A gamma intersect gamma sits below beta all the time. So the rest is above gamma. And then we have a problem. We have a problem if 2 to the L of 0 is bigger than L of 2, because then we cannot use this trick here saying, okay, look at all the countable subsets of beta. There is 2 to the L of 0 of them, L of 1 to the L of 0 of them, possibly. Oh, but that is less than L of 2. Oh, no, it's not, because the continuum hypothesis need not be true. But, and here is the good news, the proof goes through. With 2 to the L of 0 plus instead of L of 2. If you take continuum plus many countable sets, you take the ordinal 2 to the L of 0 plus, so the cardinal successor of 2 to the L of 0. You do the same thing. You take all the ordinals of cofinality omega 1 or more, for all I care. You get the same situation, and now you can go through the rest of the proof and find this delta system again. So the delta system lemma is, okay, we were a little bit over-optimistic a few moments ago, but you can save it by raising the L of 2 a little bit. You can find the delta system lemma in chapter 9 of the book, which is also on the ELO, and there you can find the general form of it. And this proof that I just gave is not completely lost with the L of 2. As you will see in the homework, you can take this proof, you don't have to do almost anything extra, and you can find another combinatorial result that is quite useful in other circumstances as well. Okay, that is what I had to say for today. And now I need to stop the recording. Do I really want to